Hi, I'm Tom, W8JI, and this video is about reflected power, return loss, standing wave ratio, whatever we want to call what's basically the same thing, and what actually happens in our systems. So I'm going to show you in a video here using good test equipment and length of coaxial cable, how all the graphs and charts that we see and this idea that reflected power is lost power or somehow goes back to the transmitter and burns up the finals and does all this other stuff isn't necessarily true. I'm going to use this chart that I pulled off the internet just as a reference, and it's not necessarily to pick on any particular person because you can find this type of data everywhere. Everybody seems to believe it, even though in a practical situation in the real world it just isn't true. So what the company here selling antennas is trying to do is they're correlating the reflected power on the transmission line with the amount of power that you're going to have radiated or have watts available, they call it, and percentage of loss. They're basing this all on the feed line standing wave ratio, but we can show in a practical demonstration that none of this applies. It only applies in a very specific case of a source that's a very particular kind of source, and where we don't try to correct the match at the source, where we just leave the source mismatched. Most of this loss that people focus on and claim is in the coax or power bouncing back from the antenna and going back to the source or whatever, most of that power is actually just setting up a standing wave on the transmission line, and power isn't going both directions at the same time. It's only going out, and this mismatch only causes a variation in impedance along the transmission line, and we can prove that that variation in impedance does not represent a certain percentage of power loss. This is my key site, ENA. It's nothing but a regular little old VNA like you can buy for $100 now, but it's of course on steroids. And while this thing costs as much as a compact car, it's still just reading the same kind of stuff that your little network analyzers, your mini network analyzers and SWR bridges and everything else. It reads just the same stuff that your stuff reads, except maybe a little bit more detailed. And so this is an idealized source. This will behave a lot like what the tables show, but that's because the source is an idealized 50 ohm source inside the analyzer, and when we have standing waves on the feed line and the impedance on the feed line changes on the transmission line between the ports, what happens is the source doesn't couple the power into the transmission line. It isn't that the power's bouncing around inside the transmission line and being all ate up and not making it to the antenna or the load because it's reflected back. It's because the source doesn't like to supply power into the load that it sees at the transmission line input. That's where the real problem is. Another thing we often get incorrect is we think that these little bridges, SWR meters, the bridges, the directional couplers, all this and that, we think that they're really reading the actual reflected power that's coming back from the load. But that isn't what they read at all. For example, look at this bridge in the MFJ antenna analyzer. While we programmed the MFJ antenna analyzer to give you things like return loss and mismatch loss and all this other stuff, reflected power, percent reflected power, while we programmed the calculations to do that, What this bridge actually measures is it measures the impedance error at the point in the transmission line where you insert it. This bridge has no idea what the standing waves really are on the transmission line. It just knows the error in impedance at the point where the bridge is inserted between the ideal impedance that the bridge is set up for. Other bridges are exactly the same way. So this is a little bridge that I designed that it measures the SWR, or reflected power, forward power, reflected power. It's a little directional coupler board that I designed for MFJ and Ameritron. The actual production ones weren't exactly like this because somebody up there changed them around a little bit. But this measures the vector sum of the voltage across the transmission line at the point it's inserted and the current through the line at that same point. So it sums these two at radio frequencies. It just sums the two things right together. One direction it adds the two quantities, the other direction it subtracts the two. And knowing the sum and the difference between those two things tells you how far you are off on impedance. But again, this particular directional coupler, while it can measure the power coming back one way and the forward power going the other way, while it can measure that, that isn't actually what it's measuring in the transmission line, because we really don't have reflected power flowing backwards into the source. That doesn't happen. What it's really measuring when it's measuring inside a transmission line with a transmitter at one end and a load at the other end, it's measuring the error in these expected quantities of current and voltage at that one point where it's inserted. You can prove, somebody can easily prove that this thing isn't measuring the standing wave ratio, directly measuring the standing wave ratio, because all you have to do is take this bridge when it's set up for a null on 50 ohms and put it in a 75 ohm line and move it along in that line. And if the bridge impedance, if the null for the bridge set up by the trimmer capacitor isn't nulled for the transmission line, for the particular impedance of the transmission line, then it's not measuring standing wave ratio at all. It's measuring the operating impedance error at that point in the line between what the bridge is normalized for and what the impedance, the operating impedance, actually is at that point. The bridge has no idea what the standing waves are on the line. Reflected power is not a backward power flow. Reflected power simply establishes a standing wave on the transmission line. The standing wave just stands in place. It represents or describes an operating impedance change along the transmission line. It's not moving, it stands there. That's why we call it a standing wave. This is the basic test setup for this demonstration. It consists of two military surplus matching networks. You see at both ends of the setup. I picked these matching networks out of all my tuners. I've got a large collection of tuners, but I chose these because they're fairly small and have very low loss. They're real easy to tune. So it's just a good matching network or mismatching network that I can use to change the impedances along the line. I have three basic power meters. All of these power meters have been calibrated to the same standard. My source, the signal source, the power source, is an ICOM 746 Pro that I'm going to set to 50 watts of carrier. This is a block diagram of the source end of things. I used a common ICOM 746 Pro transceiver to generate a 20 meter test carrier. I happened to pick 50 watts because that was full scale on the coaxial dynamics meter. The radio's tuner was disabled. I used a calibrated leader power meter into a military surplus antenna tuner, and this drove a 25-foot long LMR 400 feed line That's the sample feed line under test. That's the feed line we are going to intentionally mismatch that LMR 400 with a 10-to-1 standing wave ratio and see how much power we can get into the load, only matching at the transmitter end. This little coil of joy is the LMR 400 coaxial cable. It's just a regular old LMR 400 with UHF connectors on each end, and it connects between these two matching networks. One of the matching networks is going to set the load standing wave ratio, and the other one's going to correct the transmitter, just exactly like you have an antenna tuner in your shack on the table that you use to correct for little problems with your with your dipole antennas or whatever you're using. This is my variable load, or my adjustable load. This section is simply an adjustable dummy antenna or adjustable dummy load. Think of this as an adjustable antenna in which the actual radiated power or power applied to the antenna can be directly measured. I do that by using a coaxial dynamics power meter with a 50-watt slug right ahead of the dummy load, which is 50 ohms. So the coaxial dynamics power meter is seeing the load impedance that it's designed for. It's seeing a 50 J0 dummy load. And then how do we make this look like a bad antenna? Well, we put a little load mismatch in between the coaxial dynamics power meter and the transmission line coming up there. So this is nothing, it's just not any different than if you have an antenna system and you misadjust your gamma match or your T match or whatever you have at the antenna. You have the antenna at the wrong length or something. It's actually no different than that as far as the transmission line is concerned. The only trick to this setup is we can measure the actual power that gets past the mismatch into the antenna. So it's a very simple system that allows us to see what is actually being delivered to the. So how do we know what the load SWR is that the 25-foot LMR 400 transmission line sees? Well, that's pretty simple. We take my Keysight ENA, which is a really good fancy SWR meter, I guess you could say. But we take this Keysight ENA and connect it directly to the load mismatch tuner that we have between the coaxial dynamics power meter and the 25 feet of LMR 400. Instead of that coax being connected, we connect this Keysight ENA, and then we can adjust the load match tuner for any SWR into the transmission line at the antenna that we care to see. In this case, I'm going to first do a measurement with it at a 1-to-1 SWR to be sure everything's calibrated, and then I'm going to move the resonance of this system up out of the 20-meter band until I get a 10-to-1 standing wave ratio on the ENA. That means when we connect the 25 feet of LMR 400, it's going to be on 20 meters, it's going to be dumping into a 10-to-1 standing wave ratio load, just as if we had a 10-to-1 SWR on the antenna. The only trick is we can measure the actual power that makes it past the mismatch into the antenna. The load end of this test setup lets me terminate the test cable, in this case it's 25 feet of LMR 400, with different impedances, while still allowing me to accurately measure the power delivered into the load, which could be the antenna radiation resistance of any value. But this just is a way that we can measure the power delivered through the coaxial cable into the load when the coaxial cable under test is mismatched. In this case, I'm going to test the cable two different ways. One way is with the load adjustment matching network. so that the cable's terminated in a 1-to-1 standing wave ratio at the operating frequency. And then I'm going to change the termination so that the coaxial cable under test, the 25 feet of LMR 400, has a 10-to-1 termination standing wave ratio. And we're going to measure the power delivered into the dummy load in both cases with 50 watts applied at the transmitter end. I'm going to refer back once again to the tables that we can find on the internet or in books that try to relate a standing wave ratio at the load with a certain percentage of loss in a coaxial cable, and this is absolutely incorrect. This is not true at all for the cable loss due to a missed termination at the load. The power is not moving from the load back into the cable continuously and just bouncing around in the cable or going back into the transmitter or whatever model people try to put in their minds. That isn't what's happening at all. All the reflected power does is set up a standing wave on the transmission line where the operating impedance, the ratio of voltage to current along that transmission line, changes as we move along the line. All the power is still flowing from the source, from the transmitter or the generator. It's still flowing from the source out to the load. None of it is flowing back into the transmitter. This loss of power that shows up in these tables actually is at the source end. It's because the source is mismatched to the impedance presented by the cable, and the source simply can't deliver the rated power or the expected power into the transmission line because the transmission line no longer looks like what the source wants as a termination. So that's what that percentage is. That's why it shows up on a VNA or a network analyzer, and that's why it will not show up when we test a piece of cable and we use a matching network at the transmitter end to correct the mismatch in impedance presented by the coaxial cable to the transmitter. Once again, I'm not singling out Firestick for misunderstanding and misrepresenting what these tables mean, because it's very common. It's almost everywhere you go on the internet, and because of that, and because people form an opinion in their head of how this stuff is working, and it doesn't work that way, the misinformation is just everywhere. So we're going to focus on a 1-to-1 SWR reading on the 25 feet of LMR 400 at the load into that transmission line, and then we're going to focus on changing that to a 10-to-1 SWR at the operating frequency by adding a reactance and modifying the impedance a little bit, make it a 10-to-1 SWR. We're going to have that LMR 400 see a 10-to-1 SWR, and we're going to observe what the actual loss difference is when we go from a 1-to-1 to a 10-to-1 with the same input power and with the same cable and with only a change in standing wave ratio or load impedance terminating that 25 feet of cable. We're going to see if this table actually holds true. With the load mismatch set for a 1-to-1 SWR, looking into the LMR 400 test cable, the 25 feet of LMR 400, we apply 50 watts of transmitter power from the ICOM 746 Pro, and we see what the load power is. All of these meters have been calibrated to agree with each other before I made these tests. So let's look at what is going on now with 50 watts from the 746 Pro. The meter on the lower left is the LPM 885 meter, and we see that it's registering 50 watts of power from the ICOM 746, into the matching network at the transmitter end. That network's adjusted for a 1-to-1 SWR, so it's just kind of like a passive network. And then we see at the end of the LMR 400, we have on the Heathkit meter, on the HM2140, we see we have just a tick under 50 watts of power going into the network on the load end. Now, this loss here accounts for the 25 feet of LMR 400, and it also accounts for the loss in the tuning network that's at the transmitter. So all of those losses are accounted for in this reading right here. Now when we go through the load end antenna matching network or antenna tuner, I don't care what you guys call them, but if we go to the load end of that network into the dummy load, we see that we now have a little bit over 47 watts of power delivered into the dummy load. So in this whole system, from end to end, from the input into the initial matching network at the transmitter, through that network, through the coax, and through the power meters, and into the dummy load, we wind up with 47 watts or so of power into the dummy load under the 1-to-1 SWR condition. Now, we're going to expect, if these tables that everybody use, and if all these theories bouncing around and these people with pictures in their heads that the power bounces around into coax, we're going to expect that this loss table by fire stick, and that we can commonly find everywhere, we're going to expect that we're going to see that kind of loss when we terminate the cable in a 10-to-1 standing wave ratio and apply the same amount of power. So let's do that and see what happens. So now with a 10-to-1 SWR at the far end of the 25 feet of cable caused by mistuning the load match setup, we find that we have roughly about 10 watts of power instead of 50 watts going into the cable. So my poor little ICOM 746, because it's seeing a pretty high SWR now, has folded back and it's not delivering the 50 watts anymore, even though I didn't adjust the power setting. It's no longer delivering 50 watts into the cable. It's delivering 10 watts into the cable because it doesn't like the impedance it's seeing. It's not because there's reflected power going back into the finals. It just doesn't like that impedance that it sees when the coax is mismatched on the far end. And we also find that into the load, now we only have about 3 watts of power delivered into the load out of that 10 watts that we have at the transmitter end. So we've lost a lot of power. Now some of this is because these meters are not exactly tracking at such a low power level. I'm a long ways off full scale, so these meters are starting to be a little bit inaccurate down on the low end of the scale. You usually don't want to use a watt meter at that point. But we're doing it just because this isn't all that important anyway. I'm just showing you that if I don't match at the transmitter, things look pretty bad as far as power delivered to the load. So if we look at the Heathkit HM2140 meter, which is at the load end of the 25 feet of LMR 400, but it's ahead of the mismatch network, so it sees the high SWR at the load end of this test setup. We see we have somewhere around 19 watts of forward power and 15 watts of reflected power, someplace in that rough area. Now these meters get a little bit off when they're running into such a mismatch impedance, so we can't rely on them exactly. But I'm going to give you a little tip when you're reading power on a power meter and the meter's not it's a directional coupler type meter and it's not in the line impedance that it's designed to operate in. What you can do is you can subtract the forward power that you see on the meter from the reflected power that the meter is showing you, which isn't really power flowing backwards. It's just an artifact of what the meter's doing. But when you look at these two numbers, if you subtract them, you pretty much will get someplace around the true load power. So if we take 19 watts from 15, if we take 15 watts from the 19 watts of forward power, we see that we should have someplace around 4 watts being delivered into the load meter, because that's what the HM2140 is telling us. Now if we look at the load power being delivered into the 50 ohm dummy load after it goes through the mismatch tuner at the far end of the transmission line, and see what we have there, the Heathkit meter told us we should have around 4 watts going into the mismatch tuner, and coming out of the mismatch tuner we have around 3 watts, which seems pretty reasonable to me. So we can see that by subtracting the forward power, subtracting the reflected power from the forward power in the mismatch meter, we came out sort of close to what we really have for the real power. We're not consuming too much power in the mismatch tuner, and we wind up with 3 watts of power into the load. We don't want to put too much stock in the exact quantities of power here right now, because all these meters are running at, except for this final one that's at the load, all of the meters are running at a pretty high SWR. So they're a long ways, and they're at the low end of the scale. So they're a long ways from the calibration point where I calibrated the meters. So now I've gone back to the transmitter end of this whole setup, and I've retuned that input tuner. I don't care what you guys call it. You can fight with each other all you want on that. As long as we know what it is, I'm good with it. So I've readjusted the matching network, or the antenna tuner, or whatever you want to call it at the input end, so that my ICOM 746 Pro now sees a 1-to-1 standing wave ratio. And now my ICOM 746 Pro went right back up to delivering the 50 watts of power into the input matching network, and that matching network then is connected to the 25 feet of LMR 400, and that goes out to the mismatch load, so that LMR 400 is still running at a 10-to-1 standing wave ratio on that LMR 400. Now with 50 watts into the input end of this setup, and a 10-to-1 SWR at the Heathkit meter, which is at the load end of this setup after it goes through the 25 feet of cable, I had to change the HM2140 to the high power scale. So now we're on the 2000 watt full scale for forward, and on reflected we're on the 500 watt scale for reflected power on the HM2140. And let's look again. Remember that little trick I told you about subtracting the reflected power from the forward power to get the real power, because the meter is now in a totally wrong impedance, and the voltages and currents in the meter are just way off from what they should be. So let's do that little trick. We see we have something less than 100 watts. This meter's not going to be real accurate, because we're way down at 100 watts on the 2000 watt scale, and the meter's pretty far out of correct termination. And we see that the reflected power says that it's just below 50 watts. So if we subtract something less than, let's just say this is 90 watts. If we subtract 90 watts, if we subtract the 40 watts or so, maybe that's 50 watts, 40 watts, I don't know what, it's hard to tell down at this end of the scale. Let's call it 40 watts. If I subtract the 40 watts from the 90 watts at the in the forward power, now we're going to wind up with about 50 watts of real power in the coax. Let's remember that now this is saying that we have 50 watts of real power at the load end of the coax according to this Heathkit meter. So here we are at the load, and this is the power being delivered into the load with the 25 feet of LMR 400 cable, and is running at a 10-to-1 standing wave ratio. I'll guarantee that. And so now we see that the power delivered into the load simply by adding a tuner or a matching network, don't care what you guys call it, by simply adding the matching network at the transmitter end of that 25 feet of cable. Now the power and restoring the ICOM 746 Pro to 50 watts, of course. Now we see we deliver 42 watts of power into the load at the far end, even though that cable in between has a 10-to-1 standing wave ratio. Now this 42 watts of power includes the loss in both of the matching networks, the 25 feet and the 25 feet of cable. So we can see that we're nowhere near what what all these tables tell us that the coax loss is going to be. And this proves something. This should prove something to us, at least if we have any ability to look at this thing objectively. It should prove something to us. It proves that we don't have a bunch of reflected power bouncing around inside the coax. All that power has done is gone back into the cable and established a standing wave. All the power is still flowing from the transmitter out to the load, and all that imaginary reflected power we have in the transmission line is doing is establishing a standing wave in the transmission line that changes the impedance. It changes the ratio of voltage to current all along the length of that transmission line. That's all it does. So we can't go to a table. We can if we use a VNA at the starting end because of how the source behaves in the VNA. But this is mostly a source problem. It's not a loss problem in the cable. It's not reflected power bouncing back and burning things up and doing this and that. It's changing the impedance in the cable, and it barely changed the loss in the cable, going from a 1-to-1 standing wave ratio to a 10-to-1 standing wave ratio. So at the load end of this setup, we now know that we have around 42 or 43 watts of power delivered when that coax is running at a 10-to-1 standing wave ratio. So that really flies in the face of all these tables that tell you that you should have, significant power loss in the cable from a 10-to-1 standing wave ratio. At the load end, if you remember right, when we started out, we were around a 47 watts at the load. So we've gone from 47 watts at the load to maybe 42 or 43 watts because of having a 10-to-1 standing wave ratio on that 25 feet of LMR 400 cable. So while the table predicted that we're only going to deliver about 33% of our transmitter power to the load, we actually delivered around 91%. Now this is going to vary with the type of cable and how long the cable is and everything, but it shows that these tables are really being misused. Now all of this stuff in this video is good engineering, it's good common sense, and it's the way it really works. I suggest if you have some problems with this, you get a copy of Reflections. You go online, you can find it somewhere, by Walt Maxwell. Walt's a silent key right now, but Walt was trying to do a real good thing for the amateur community and get rid of all these crazy myths about standing wave ratio. Unfortunately, Walt fell victim to really a small argument about conjugate match. And to tell you the truth, I looked at this stuff with a bunch of different transmitters and using different ways to measure the standing waves on the line. And Walt's statements were really close to being exactly spot on, and the detractors of Walt were a mile off. So what I suggest is that you go back, everybody go back and read a copy of Reflections and try to understand what Walt's saying. If conjugate match sticks in your craw, then ignore it. Don't focus on what it means. Don't try to focus on what the source looks like. Just forget about that and just look at how the transmission line behaves. And you'll find out that antenna tuners, transmission lines, and standing waves behave exactly like what Walt W2DU, who's now a silent key, it's exactly like what Walt was trying to tell everybody, but unfortunately his book kind of got pulled from ARRL good graces because of a lot of pressure because of the conjugate match controversy. So let's stay out of the conjugate match controversy and just look at how the transmission line behaves, and we'll all find that Walter Maxwell was correct in what he was saying. Thanks for watching this video, and I hope this helps clear up some of the baloney about standing waves.